All right, guys. Can you guys hear me? Can you guys hear me? All right, so let's give it one more minute while we're receiving more students. Here's the first lecture of our new session. So we might have some students who have some technical issues, so on and so forth. So let's give it one more minute while we're receiving more students. Okay. All right, I think we can get started. Okay, welcome guys to our number theory lecture. So before we get started, since we have some new students joining us, I just want to have a quick kind of like a warm-up stuff about our lecture. So our lecture actually focuses on the North American math competition. So apparently it's a math competition course. So as you know, the math is actually a very practical course, right? You really want as many interaction, as many practice as possible. So therefore, during the entire process, I really want you guys to get involved into the lecture. I want you guys to basically interact with me as much as possible. So in terms of camera, you can turn it on, you can turn it off. It totally is up to you. So if you want to turn it on, you might have more interactions with me. You can see my face. I can see your face. If you want to turn it off, it's okay. It's up to you. You have more privacy. So there's no obligation, right? You totally have the rights. And also during the lecture, I want you guys to interact with me. You have two ways to do the interaction. You can always like unmute yourself. As long as you enter the classroom by default, you put it into mute. However, you can always unmute yourself. You can answer a question, you can raise a question, so on and so forth. Feel free to do so. Or alternatively, we have our group chat functionality. You can always chat with me privately or publicly. So while the lecture is ongoing, I'm always monitoring our group chat. So any question, just let me know. So I'll be able to help you out. Okay, this is basically, we want to have more freedom, more interactions for the lecture, which is very important. All right, if all good, let's get started. Let's go to our lecture, number theory. All right, so I have to say, as long as people see the title number theory, they might be a little bit scared. Okay, number theory looks like something difficult, looks like something, a lot of formulas, a lot of properties, so on and so forth. Yeah, it is yes and no. Yeah, to be honest, the number theory is one of the most complicated part in the North American math competition. Because most of the concepts we'll be testing here, you won't be able to learn that in your day school. So that's actually basically give a gap. So you really have to do some extra learning in order to take out all those number theory related problems. So this is actually on the kind of like the difficult side. Well, on the other side, number theory, it basically comes from number, right? So even though you might not have a very systematic, very comprehensive understanding about number theory, but most of the basic concepts of a number theory, you should already learn that even from your elementary school. So, you know the prime numbers, the composite numbers, right? You know the divisibility, some number divides another number. Sometimes you got a remainder, so on and so forth. So these are actually considered to be the foundation, like the basics of the entire number theory. So that being said, in our lecture, this 10 lectures, we're going to be giving you guys a lot of like a common sense stuff. And taking from there, we're going to elaborate a little bit. So try to give you some more interesting concepts, more interesting conclusions based on the common sense. So that's going to be a more interaction process. So always let me know whenever you have any questions. Feel free to interrupt me, or you can basically send me a short message, like the group chat short message. So I'll be able to see, okay, somebody has a question, I'm going to stop it and then help you guys to figure out the problem. So this is basically where we come from. Okay. And another thing is, please do me a favor. If you have like your name or something, please try to change your name into the name you did the registration. So I'll be able to do a comparison, who is who. If you have a lot of like fancy names, I won't be able to tell who is who. So please do me a favor, okay? So put your name into the way you register in the class, that I'll be able to see you. All right, so if all good, let's jump to kind of like a warm up about our number theory. So like I said, number theory, it basically comes from the number, right? So people are actually talking about the number for a long time. This is like an old topic, right? Back to the ancient Greek, there are so many mathematicians, they were talking about numbers, right? We find so much, integers, whole numbers, positive, negative, prime, composite, all those kind of like numbers. And number theory, the name speaks for itself, is actually a technology try to find out the properties of a number, right? So we're trying to find out the properties of numbers, okay, which is quite understandable. So if you have a good understanding about a number, you should basically try to understand more properties of the number. So actually, the famous mathematician Gauss has already give a kind of like evaluation, kind of like a comment about the number theory. So Gauss says, mathematics is the queen of science, and number theory is the queen of mathematics. So that means that you'll be able to see, number theory is like so important. A lot of mathematicians, even though they might have their focus, there might be a geometrist or there might be an algebraist, but at the end of the day, they still like to contribute part of their time talking about the number theory, because number theory is kind of the holy place. Let's put it this way, kind of like the holy place in the entire mathematics. So everyone, especially the mathematicians, wants to do some contribution. So as long as we talk about the number theory, I think there are some very famous mathematicians we like to talk about. You're going to see their names, from all over the places. Different kind of number theory principles or theorems, you're going to see their names from time to time. So at the very beginning, let's have some quick talk, like a warm-up, like some gossip. So what are the famous mathematicians we need to remember talking about their contribution to number theory? The first one is Euclid. Euclid is a very famous name, right? Our Waterloo math competition, especially grade 12, the grade 12 math competition is actually named after this famous mathematician. And Euclid, he's actually a geometrist, right? He spent so much time in his life trying to find out the basic properties of our 2D geometry. And that's the reason why our 2D geometry, sometimes we call it Euclidean geometry, right? So this is actually the main contribution, the major contribution of Euclid. However, Euclid also contributes a lot for the entire number theory. For instance, he found out the prime number is infinitely many. Okay? He found out like so many prime numbers, and there are infinitely many prime numbers. This is actually a very good find out, because these days, I don't know if you guys heard about this or not, we're still trying to find out the biggest prime number. So every year there's a prize offered, just try to find out who find out the biggest prime number ever. So, there's kind of like a competition. Of course, these days, no one trying to find out manually. They use the computer to calculate what is the biggest prime number ever. So he actually contributes a lot for, finding out actually there are infinite many prime numbers. And also he actually introduced the famous fundamental theorem of algebra, and he talked about the factorization. For any given positive integers, the factorization is always unique. Let's say I have a number p, for instance. I want to do a prime factorization. Let's say P1, P2, all the way to PK, for instance, right? So I want to say that actually, if you have an integer, and you want to do a prime factorization, this prime factorization is always unique. So that being said, you give me a prime number today, or you give me a composite number today, I do a prime factorization. Today, I have P1, P2, P3 are the factors. Tomorrow, I'm still going to have P1, P2, P3 are the factors. So there's no way for the prime factorization to be changed. So prime factorization is unique. So that being said, it is valuable. We spend some time talking about the prime factorization. Okay. And the other name I think we want to talk about is format. Format is also, a math competition's name, right? Our Waterloo math competition grade 11 was actually named after Fermat. Fermat is actually a very famous mathematician. He actually find out two things for the entire number theory part. One is what we call Fermat's little principle. We will talk about the Fermat little principle in our lecture. So for now, we don't have to spend too much time. So this is actually a very important principle which tells you the relationship between the exponents, between the prime numbers, and the remainder, so on and so forth. We'll talk about it. We're getting there. And the other one is actually the famous Fermat last principle. Why we say last principle? This was actually raised at his later age. So this is kind of the most important principle he raised, in his elder age. So we call this is the last principle. He actually has some other principles afterwards, but I think this is the most important. So we give a name, last principle. So the Fermat last principle is actually one of the most important principle people like to give a proof. You know what? In our entire mathematics, right? As long as you got a principle, you need to have a proof. You can't just basically think, okay, I think this one is going to work. That is only considered to be conjecture, right? Conjecture means the things is people believe is correct, but we never have a rigorous proof. Principle, theorem, these are considered to be already successfully, rigorously proved. So Fermat, the last principle was actually raised by Fermat as elder age, and he claimed that he already gave a proof. However, due to the limited space, he does not have so much scratch paper, so he just ignored the proof. This is actually what he claimed. However, after Fermat passed away, people just can't find any information, any evidence that he ever proved the principle. And it was actually after almost 300 years, English mathematician from Oxford, he actually provided a real proof. His name is Andrew Wiles. Okay, Andrew Wiles. He actually gave the proof, I think, in 1995, almost 300 years after the Fermat last principle was actually raised. So by the time then, when the journalist gave a kind of interview with Andrew, the journalist is asking something like this. So now you actually prove the last principle, which Fermat claimed to prove 300 years ago. So how do you think that our normal people, our modern people, we spent 300 more years trying to prove a principle that Fermat claimed to prove 300 years ago? So actually, Andrew's answer is also very diplomatic. You just say that this is actually a 20th century solution. So it can only be proved in 20th century. So that being said, he believes that Fermat didn't really get a proof. He just claimed maybe he's cheating, right? So he was lying, that he didn't really prove the principle, but Andrew Wiles, after 300 years, finally get a proof. And that makes a significant contribution for our entire mathematics. And his contribution for the entire number theory is very important by proving the Fermat's last principle. This is actually something very important. Another name I want you to remember is Euler. Euler is also a very famous mathematician. And actually, Euler proved many interesting things. First, Euler actually gave the proof of the Fermat's little principle. Okay, you see, Fermat basically reads the principle, but Euler gives the proof for the little principle. And also, trust me, Euler actually did a lot of significant contribution for mathematics. For instance, Euler's kind of like our mathematics science, let's say fx, stands for the function, right? That was actually raised by Euler. Let's say sine x, cosine x, tangent x, all those kind of trigonometry symbols were actually raised by Euler. So without Euler, people won't be able to use such nice little brief symbols. Still, people are going to maybe use a long sentence to present this is a function, this is a sinusoidal function, this is a tangent function, so on and so forth. And actually, Euler did a lot of interesting contribution for our Diophantine equation and its solution process. Diophantine equation is also a very important part in our number theory. If we have some time for our lecture, we're going to introduce a little bit how the Diophantine equation looks like and what are the important properties of the Diophantine equation. Okay. Yeah, and also the last one I want to talk about is Goldbach. I think that part everyone knows that, right? Goldbach congestor, right? That's a very, very famous congestor. Why we call it congestor is because today people didn't really get a solution, didn't get a rigorous proof for the Goldbach congestor. So it is still considered to be congestor. And actually one of our Chinese mathematician Chen Jingren did a significant work for the proving process of the Goldbach congestor. He basically, you see, Goldbach sometimes we call it 1 + 1, right? And Chen Jingren actually did it to 1 + 2, just like a one step forward, and he'll be able to have a full solution for the Goldbach. So I'll say that, like the future is yours, right? So maybe someday, one day, you guys can actually contribute to really push Chen Jingren's solution a little bit forward, find out a rigorous solution for the entire Goldbach. So as you can see, a lot of like famous mathematicians, they put a lot of emphasis. They do a lot of like interaction with the number theory. So that being said, number theory is like so important. So everyone needs to basically learn something from number theory and try to contribute something to the number theory. All right, this is kind of like a little warm up, go say things. So why number theory are so important? Because there's so many mathematicians, they contribute for this number theory. And this is actually the entire foundation of the mathematics. All right. And talking about these kind of like big things, let's try to be a little bit focused about our stuff. So number theory, like I said, is actually one of the most important concepts in the North American math competition, American and Canadian, so on and so forth. And there are many concepts from there. We need to give you guys, the definition of different concepts. We want to talk about the classical problems. And most importantly, we want to teach you guys the solution strategy, how to solve the problem. Fish and fishing. Of course, fishing is more important. So the focus of our lecture is try to teach you guys this kind of different methodologies, different tricks, how to solve a number theory related problem. So this is the syllabus of our lecture. So we can give you like a quick walkthrough to see what we're going to talk about for our entire lecture. We're going to get started talking about the divisibility and its corresponding important properties. That's actually our today's lecture. Divisibility, this is something what you know, right? So 6 can be divisible by 3, right? 3 is a divisor of 6. This is what you learn from like elementary school. But today we're going to give more interesting properties about the divisibility property. And then later we're going to talk about the prime numbers and composite numbers. Also, you guys learn about it. Like I said, number theory, the majority of this part, you must have some foundation, some basic concepts. But now we're going to give you more flowery properties, more interesting elaborations. Then we're going to talk about the greatest common divisor, least common multiple. We have already talked about it. We have already learned from your early age. And then moving forward, we're going to learn a very important concept we call the modular arithmetic. So this is actually considered to be the foundation of this entire number theory. This entire number theory topics, they're actually created or elaborate from the modular arithmetic. Having a good understanding for the modular arithmetic is going to be extremely important for the number theory related learning. And then we're going to spend some time talking about 3 very important number theory theorems. They are Fermat Little principle, Euler's torsion formula, and Chinese remainder theory. So trust me, these 3 parts, the American and even the Canadian math competition is going to test it from time to time. So having a good understanding for these 3 formulas, 3 principles is going to be crucial for our North American math competition study. And then if we have some time, we're going to introduce some advanced number theory theorems. So these theorems are not compulsory. So if you really do not have too much time, you can ignore them. However, if you know some of the theorems, it's going to help you to expedite this entire solution process. Sometimes people use 5 minutes, but you use 30 seconds and you can solve the problem. So if you have some bandwidth, some time, let's have some quick discussion for that. We're going to talk about the number base. You know, we're so familiar about this decimal, right? We use 10 as the base. All those Arabic numbers, right? We're basically doing that. And if you're familiar with the computer stuff, you know, computer is actually based on the binary system, right? We're using 1, 0, 0, 1, different kinds of combination, basically to have your this entire architect being created. And also, you know, sometimes we use the hex. Hex is basically, you know, if you use your calculator, sometimes the calculator has a hex, right, for the base. So hex can also help you do a lot of like scientific or numerical calculation, help to make your calculation a little bit more straightforward. So these are something very special and very familiar for most of the students. And on top of that, we have some other bases. Now, what about I use 3 as base, 4 as a base? I even use a k as a base. Is there any special properties I can do conversion between the regular decimal or binary into the k base and vice versa? What are the flowery properties between the two? So these are also something we like to talk about. We're going to talk about something about the factorization or factor-related theorems. Like I said previously, the Euclid find out for any given number, positive number, negative number, whatever, you can do a factorization. And this factorization is unique, right? So as long as you have something unique, it is valuable that let's try to do some analysis, try to figure out the properties of the factorization. And also, we're going to talk about the Diophantine equations and their basic properties. Diophantine equation is kind of a special equation, and there's a lot of interesting applications for the Diophantine equation in the number theory part. So let's have some quick talk about the Diophantine equations. All right, so this is kind of like a big syllabus, a big outline what we'll be talking about in our number theory lectures. Do we have any questions? All good? Yeah, any questions, just let me know, okay? If all good, let's jump to our first part. Let's talk about our lecture number 1, divisibility. Okay, divisibility is actually our lecture number 1. So what is a divisibility? I think divisibility is something like so understandable. For instance, 6 divides 3 is 2. But 5 divides 3, you can actually have 1 as the quotient, and then you have 2 as the remainder, right? So this part, I think everyone knows that. So now, if we go to the definition, let's try to use some mathematical language to put these kind of very understanding, very easy peasy concepts together. Let's have some quick look at it. How the divisibility is defined from a mathematician's perspective. An integer b is divisible by an integer a. Of course, a cannot be 0, right? If you use something as a divisor, the thing cannot be 0. So we write, if b is divisible by a, we write something like this: A pipe B. Okay, we write like this. This is only a denotation. So we put a divisor on the left, and then we put a pipe. The pipe is more like our division sign, right? But anyway, it's kind of like a flat. This is like straight pipe, and then B. So we write like this. When we want to write this, if there is an integer x such that B is equal to A times x. Okay, this is something so easy, right? B can be divisible by A if you can put B equals to A times x. Of course, x is an integer, right? So in that case, we want to how to say that, right? We want to read this sign as A is a divisor of B, or B is divisible by A. Is that right? So this is, you learn that from elementary school, right? A number can be divisible by the other number, you use, or the other number is a divisor of this number, you basically write B equals to A times X. And for our number theory's perspective, we want to give something like this. A pipe B means A is the divisor, B is the multiple of A, right? This is something so easy. So as we can say, let's say 3 is a divisor of 12, right? Let's say 10 is a divisor of 100, or minus 3 as a divisor of 6. You know, you can write as many as I like, right? So this divisibility can be between the positive numbers, negative numbers, as long as you follow such a relationship, which is so understandable. That's the definition of divisibility. Because this is so easy, so let's try to see some properties, how the divisibility works. So let's say we have like M and D. They're both, or they're all integers, okay? So the following property really holds. First one, n is a divisor of n. Of course, 10 is a divisor of 10. 100 is a divisor of 100. Any number is a divisor. Any number is a divisor of itself. Or we can say any number is divisible by itself. So easy. Second, if D is a divisor of n, but n is a divisor of m, so I can say D is a divisor of m. For instance, 2 is a divisor of 6, right? 6 is divisor of 12. So therefore, 2 must be a divisor of 12. So that being said, this divisibility property can be passed on, right? You can pass on this property to different forms. As long as you have, this is the number here, the number here, you can actually pass it on, which is also understandable. Number 3 is an important property. D is a divisor of n. D is a divisor of m. Then D must be a divisor of an plus bm for all the a and b's. Of course, a and b must be integer, right? Because a, b are integers. What is that? I'll give an example. Let's say, number 3, I'll give an example. Let's say 3 is a divisor of 6, right? 3 is a divisor of 9. So that being said, 3 must be a divisor of 6x plus 9y, as long as x, y, they are integers. Does it make sense? Any kind of like combination between 6 and 9, they must be also divisible by 3. If you do not agree with me, this is actually something very understandable. I give an example. Let's say 3 is a divisor of 6, 3 is a divisor of 9. So therefore, anything you times x, anything you times y, 6x and 9y, they're still divisor of 3, right? You're adding 2 things together are still divisor of 3. So that being said, if you have D is a divisor of 2 numbers, m and n, then any combination between m and n, you times another integer, you put another coefficient, so on and so forth. If you do them together, adding them, subtracting them, so on and so forth, also going to be divisible by d. Trust me, this looks like a very easy peasy, very understandable property, right? But trust me, this is going to be something so important. You're going to see a lot of interesting applications based on this property. Especially when you go to higher grade, you're going to see more and more interesting problems you're going to use in such a property. In our grade, maybe you won't see that much, but it is so valuable that we like to bring it up. Let's continue. I think the divisibility properties are so intuitive. You learned it like a long time ago. Let's say number 4, what's going to happen for number 4? Let's say d is a divisor of n. And then on the two sides, if you multiply the same thing, AD must also be a divisor of AN. 3 is a divisor of 6, right? If you times 2 on two sides of this pipe sign, then 2 times 3 must be a divisor of 2 times 6. 6 is a divisor of 12, which totally makes sense, right? Okay, as long as we have this multiple, maybe people think about, can we have this division, this cancellation property? Yes. AD is a divisor of AN. So therefore, of course, A can't be 0. It cannot be 0. If I divide A on the two sides of this pipeline, the conclusion will also be correct. D must be divisor of N. Give an example. 2 times 4 is divisor of 2 times 16, right? 8 is a divisor of 32. So you both have 2 on two sides of this pipeline. You cancel this, you cancel this. 4 must be a divisor of 16, which is totally understandable. So here, these two properties, it's kind of like a twin brother. The two red properties. One is what we call the multiplication property. You can multiply them together. The other one is what we call the cancellation property. You can cancel them one after another, right? So this is something quite understandable. Let's continue. These are very common sense stuff, right? So another one, 1. 1 is a divisor of everything, right? Any number can be divisible by 1, even 1 itself. Number 7, if n is a divisor of 1, even though 1 is a divisor of everything, but 1 does not have too much divisors, right? If a number can be a divisor of 1, then that being said, this number can only be two options, either positive 1 or a negative 1, which makes sense, right? There's not too much flexibilities for a number which is the divisor of 1. Number 8, D. Any kind of numbers is actually a divisor of 0. This is more like a definition. Because like I said, in your number theory related discussion, of course you want to have, zero discussion, right? You do not want to have any zero related discussion. We want the divisors all 0. We want all the other numbers non-zero. So that's going to make our life a little bit easier. However, to try, for the sake of being complete, people want to give such a definition. So D is a divisor of 0, means everything divides 0. And another thing, similarly, is number 9. 0 divides n. If 0 divides n, then we define n must equal to 0. Because normally speaking, you never say this, right? 0 is the divisor of 3. This is wrong. Because 3 divides 0, this is not something we learned from our elementary school, right? However, for the sake of being complete, people defined, okay, if I really want to say 0 divides a number, then this number must be 0. So you can say that 0 defines 0 over 0. This is something meaningful. But again, this is more like a definition as well. So if you do not really want to spend too much time understanding why 0 can be a divisor for now, you can just basically remember this is a definition. There's no reasoning. We just have such a definition. Okay, so these two parts is more like a definition. It has nothing to do with the real calculation or the real property. Just try to be complete so people just put it together. Okay, and the last property, if d and n, they're positive, and d is a divisor of n, then of course d will be lesser or equal to n. Of course, a number's divisor, if we're all talking about the positive numbers, a number's divisor will be for sure lesser or equal to itself, right? For instance, 4, if I find a divisor, who is 4's divisor? Can be 1, 2, 4, right? So all those numbers must be lesser or equal to itself. Who is the divisor of 3? So it's only 1 or 3, right? So of course, a number's divisor will be always lesser or equal to itself. These are so easy peasy stuff, right? So I'll be surprised if you do not understand any of them, right? This is quite understandable. So another thing I want to talk about is that actually in our number theory related discussion, most of the time, we just talk about positive numbers. Positive integers, because the negative one, there's only kind of like a sign difference, right? So normally speaking, if I want to say, okay, tell me what are the divisors for, you just give me the positive ones, they're good enough. Okay, what's the divisor of 3? You just give me the positive ones. Unless specified by the problem, by default, we always focus on the positive divisors. Okay, this is kind of like a mutual agreement for the entire mass. All right, so this is actually number 1 we talk about. We say that this is the divisibility property. What are the property of divisibility? For our grade 10, our like a regular AMC 10 or KD, our kind of like a lower grade, there's another very important property I like to share with you guys. That is the divisibility rule. So what is the divisibility rule? Means what are the numbers that can be divisible by 2? So what are the numbers can be divisible by 3, by 4, by 6, by 7, by 8, so on and so forth. We need to find out the property of certain numbers. They can be divisible by other numbers. So these are what we call divisibility rule. Try to find out the pattern. Try to find out the property for a certain group of numbers who could be divisible by 1, 2, 3, 4, 5, like whatever. Again, some of them are very intuitive. Let's have some quick discussion together. What are the property of the numbers which can be divisible by 2? A number can be divisible by 2 means there are even numbers, right? Even number means what? Means the last digit is even, right? Easy peasy. The last digit of a number is even, means it's an even number, so this number must be divisible by 2. What about a number could be divisible by 3? A number could be divisible by 3. I think you guys learned that from your elementary school, as long as the sum of all the digits is divisible by 3. So this number is going to be divisible by 3. Is it right? For instance, I give you a number 1, 2, 3. This number for sure could be divisible by 3. Why? Because the total sum, 1 plus 2 plus 3 equals to 6. 6 could be divisible by 3, so this number could be divisible by 3, right? A number can be divisible by 3 if and only if the total sum of all their digits add up to a number which could be divisible by 3, so the original number would be divisible by 3. Easy peasy. Let's continue. Number 4, what are the numbers that could be divisible by 4? If the last two digits of a number are divisible by 4, so this number could be divisible by 4. What does it mean? Means if I give you a number, regardless how many digits, let's change the color to black. How many digits, I don't really care. It can be 2 digits, can be 2,000 digits. But as long as the last two digits of this number could be divisible by 4, let's say last digits is 1, 6. Then the previous ones, I don't really care. You can be whatever you like. As long as the last two digits can be divisible by 4, this number must be divisible by 4. Okay, try to remember this. Maybe this is not as familiar as the first two, but take this chance, try to remember it. All good? Okay, let's continue. What are the numbers could be divisible by 5? That one is easy. A number could be divisible by 5. You just have to check the last digit. Again, right? The first digits, I don't really care. 1,000 digits or 1 million digits, I don't really care. I just check the last digits. If the last digit is either 0 or 5, so this number is guaranteed to be divisible by 5, right? Again, 4 and 5, they're similar. I don't really care the previous numbers. I only care the last number. The last number is 0 or 1. The other ones, I don't really care. Okay? Oh, good. Let's go to number 6. What are the numbers that could be divisible by 6? A number could be divisible by 6. It has to basically follow the first two. As long as it follows the rules, can be divisible by 2, and it follows the rules, can be divisible by 3, then automatically it could be divisible by 6. So if the number is divisible by both number 2 and number 3, a number divisible by 2 means the last digit is even. A number divisible by 3 means all the digit sum is actually divisible by 3. So therefore, a number divisible by 6 means the last digits must be even. I don't really care how many digits, right? The last digits must be even, plus the total sum of all the digits must be divisible by 3. So therefore, this number should be divisible by 6. All good? Okay, let's continue. Number 7. What are the numbers could be divisible by 7? This is a little bit tricky. Maybe you do not see that very often. So how can we evaluate the number can be divisible by 7? If the last digit of the number is doubled and subtracted from the rest of the number, and the difference is divisible by 7, so this number would be divisible by 7. What is that? I'll give an example. Let's say 2 to 4. Let's have a look at if this number is divisible by 7 or not. So what we're going to do, if the last digit of the number is doubled, 4 doubled, we go to 8, right? And subtracted from the rest of the number. So the rest of the number is going to be 22, right? You have 3 digits at the very beginning. Now you remove 1, so still you have like 22. If you do a subtraction, this guy, 14, right? If the subtraction, the difference is divisible by 7, the original number will be divisible by 7. Okay? I give you a number. This number can be whatever digits. Again, I don't really care. It can be 1, 2, 3, 4, right? Whatever digits. You only care about the last digits. You use the last digits times 2 and then subtract the previous digits. If the difference is going to be divisible by 7, so therefore, this number should be divisible by 7. Another example, I'll give you another example because this one is not very common, right? Another example, maybe I write it here. Let's say 133. 133. Is this guy divisible by 7 or not? Last digits doubled, go to 6. The remainder one, I'm going to put it here. 13 minus 6 is 7. 7 is divisible by 7. So the original one, 133, is going to be divisible by 7. So far, so good? Can I have some feedbacks? Are you all with me? Yes or no? You can type from the group chat. Then just try to make sure we're all on the same page. These are just some basic, kind of like a basic, interesting property, and you can try to remember it. Nothing too special, right? You just have to remember. Let's go to number 8. So a student got a question, what if the result is negative? Okay, the result is negative, it doesn't matter because the question just says the difference between the two. I don't really care who divides who, right? Who is the first one, who is the second one? I don't really care, right? So that's actually something we can do. Okay, let's go to number 8. What are the numbers which are divisible by 8? Okay, a number divisible by 8 if the last 3 digits of a number, they are divisible by 8. So these number would be divisible by 8. 1, 2, 3, 4, 5, right? I don't really care. But as long as the last 3 digits can be divisible by 8. Let's say 0, 6, 4, right? This one is the last 3 digits could be divisible by 8. Okay, so this number is going to be divisible by 8. Okay, all the way from here, let's have a quick recap. What are the properties about this 2, 4, 8? 2, I want to make sure the last digit is even, aka the last digit divisible by 2. This number will be divisible by 2. 4, the last 2 digits divisible by 2, divisible by 4. So this number will be divisible by 4. 8, the last 3 digits divisible by 8. So this number would be divisible by 8. If you see the do you see the pattern? 2, you just ask 1 digit, last 1 digit divisible by 2. 4, last 2 digits divisible by 4. 8, last 3 digits divisible by 8. So if I really want to ask you, what are the properties for 16? The numbers divisible by 16, who can tell me what's going to be looking like? What is the property we'll be looking at? Please post your answers into the group chat. This is not a rocket science, right? You see 2, you see 4, you see 8. Who can tell me what's going to be if I ask you, what is the property for a number which is divisible by 16? What's going to happen? Who can tell me? I'm going to ask maybe Diana?
Me?
Yeah.
I just said in the
Oh,
chat.
Diane. Sorry, Diane.
Divisible by 16.
Is that right? Yes. Will be the last 4 digits. Right? The last 4 digits divisible by 16. Then you will be able to have a number divisible by 16. So same thing, 32, 64, so on and so forth. You can use the same pattern, right? So that's the reason why. So whenever you learn something, you need to find out a pattern. So sometimes the teacher only give you 1 or 2 examples, but the following part will be exactly the same. Okay. So 8, we're done, right? Let's go to 9. What are the properties for the number divisible by 9? If the sum of the digits is divisible by 9. The sum of all the digits is divisible by 9. Again, I also want to give you guys a quick comparison. This is 9, right? What is property for 3? 3 means the sum of all the digits is divisible by 3. 9 is the sum of all the digits divisible by 9. So what about if I ask you 27? What is going to be? What will be the numbers divisible by 27? What would be this number looks like? Who can tell me? You check 3, check 9, you can guess out what's going to happen for 27. Who can tell me? Who can tell me? I'm going to ask maybe Camila.
I also just typed in the chat, actually. It's the sum of the digit is divisible by 27.
Right? Yes. Sum of all the digits divisible by 27. See, the same logic. You always need to find out a pattern. Okay, we're done for 9. Let's continue. Divisible by 10, that one is easy, right? A number ended by 0 will be divisible by 10, right? That one is easy. But what about 11? What about 11? This part is going to be something new. You need to basically learn this. What is the property for a number which would be divisible by 11? If the difference of the alternating sum of the digits is a multiple of 11, so this number would be divisible by 11. What is that? Let's say 1, right? This is 11 squared, right? 121. The sum of the difference of the alternating sum. Alternating sum means these are all the even digits, right? 1, 3. This is the first one, the second one, the third one, right? So these are alternating, right? All the even digits, adding them together. All the odd digits, adding them together. And then you make a difference. This one adding together is 2, right? 2 minus 2 equal to 0. Of course, 0 is divisible by 11. So therefore, this guy would be divisible by 11. Another example, let's say, give another example. Let's say 1078. These are what? These are the odd digits. These are the even digits, right? 7 plus 1 equals to 8. 8 plus 0 equals to 8. 8 minus 8 equals to 0. So this is also divisible by 11. So therefore, 1078 is also divisible by 11. Okay, 2 examples I think will be good enough, right? If I give you a number, how to evaluate this number is divisible by 11 or not? You just alternatingly doing the sum. All the odd digits, adding them together, all the even digits, adding them together, you make a difference, and then you'll be able to see if the difference is divisible by 11, the original number will be divisible by 11. Okay. And last one, what about 12? A number divisible by 12. So basically, you just want to make sure the number is both divisible by 3 and by 4. You know the 3 property, you know the 4 property. So like a number could be divisible by 12 means the sum of all the digits equals to 3, and the last 2 digits can be divisible by 4. That's it. So of course, you can keep writing, right? You can write 13, 15, 16, but normally speaking, we won't ask you something too flowery. As long as you know the first 10 numbers, that should be good enough. Now I give you 12 numbers and some extra, 16, 27. So as long as you know this, generally speaking, it would be good enough. So far, so good? I think this is quite understandable, right? Perfect. So these are basically all the concepts. You know, we introduced the basic concept of divisibility. We talk about the divisibility rules. And before we jump to the problems, let's try to do a quick summary. So what are the typical problems you might be looking at? Or what are the common strategies you need to use whenever you go to the divisibility part in the North American math competition? So like I said, fishing. Let's talk about some fishing part. Common strategies. What you need to do, normally speaking, what will be tested in the North American math competition when they're talking about the divisibility part. So there are a few things I think you need to remember, which will be tested from time to time. Number one thing is you need to know to do a factorization. As long as people are talking about the divisibility, talking about a number can be divisible by another number, I think number one thing you need to think about is try to do some factorization. Even the divisor or the big number, try to factorize them. Try to see what would the properties, for instance. I give an example. Let's say AB is divisible by A squared B square, something like that. So your first reaction is, okay, AB can be write as A times B, right? A squared, maybe A squared B squared, A times B times B, right? So as long as you have some numbers, this is not a prime number, maybe you can try to do some factorization. So for instance, I say 4 is divisible by, I don't know, 64, for instance. So that being said, 4 is 2 to the power of 2, right? 64 is 2 to the power of 8. Try to do some factorization. Hopefully, after the factorization, you can make our life a little bit easier. This is a common strategy. People keep seeing that in our kind of like AMC 10, Cayley level math competition. Second part is basically our divisibility rule. So sometimes people might give you some condition saying some numbers could be divisible by a certain number. So this is basically what we just introduced. You need to remember the divisibility rule by heart. Okay? I think most of them are easy, but some of them maybe 7, maybe 11, they're not so familiar. So get yourself familiar with those divisibility rules. That's going to help you a lot in the math competition. Okay? That's the second part, divisibility rule. Third part is, in most of the divisibility related problems, you need to do some casework. Casework is more like, I think people talk more casework when they're talking about the counting probabilities, right? But trust me, in the divisibility related problems, you also need to do a lot of casework. Try to break them into different scenarios and then try to find out, the pattern for different scenarios. And hopefully taking from there, you will be able to get what you need. Maybe this is a little bit vague. You do not really know what I'm talking about, but no problems. This is more like a high level, strategical solutions, strategical directions. Later, I'm going to give you some real problems. You would be able to get a hang of it as long as you are basically doing the real problems. Okay? So that's, I'll say these are the basic, the most important properties you need to know and the most important strategies you need to deal with when you are talking about the divisibility related problem. All right, if we're all good, it's time to see some real problems. Okay, I'm going to give you some problems from the American, Canadian, even other national, different math competitions to help you guys to see how to use the technologies we introduced in our lecture, try to solve the real problems. So let's just go to category number 3, problems. Okay, so let's get started. Oops, I'm going to chop this. For the library. Right. Let's go to our question number 1. Our question number 1 is a problem that comes from 2001 Katie, question number 18. Katie, question number 18. Katie is for grade 10, right? It's the Waterloo exam for grade 10. So let's have a look at it, how we're going to do such a problem. The problem says, how many 5-digit positive integers? As long as you read the problem, you need to highlight the buzzword, right? Like the action words. 5-digit positive integer. Like I said, most of the time, people just only ask you to do the positive. No need to do negative. How many 5-digit positive integers divisible by 9 can be written only using the digit 3 and 6? Okay, I have a bunch of 5-digit integers. They should be divisible by 9. And they must be only composed using 3s and 6. You can use the other digits rather than 3 and 6. For instance, right, you can use 3, 3, 3, 6, 6. I don't know this one is going to be divisible by 9 or not, right? This is one option, and the other options, so on and so forth. Okay, so let's have some analysis. How are we going to deal with such a problem? Okay, we need to use all the knowledge we learned to try to solve the problem. 5 digits positive integer, okay, nothing to say. Divisible by 9, okay? Who can tell me? We just learned the divisibility rule. According to our divisibility rule, what are the properties that a number could be divisible by 9? Still remember? Still remember? Alex? Alex 1?
If all the numbers are added up to be, or all the sum of the digits is divisible by 9.
Right. A1 plus, let's say this number, I'm going to put it in this way. Yes. I'm going to say it's only 5 digits, right? A1, A2, A3, A4, A5, right? Maybe this is my number. So the only thing I need to guarantee is A1 plus A2 plus A3, A4, A5 equals to like nice multiple, right? I'm going to maybe divide this. 9 is divisible by you basically adding them together, right? Okay, that's the second condition. Well, the third condition is A1, A2, all the way to A5. These can't be random numbers. They must be only 3s and 6, right? I'll say AI belongs to 3 and 6. Is that right? AI must belongs to 3 and 6. So that being said, who can tell me? Now I have 5 digits. I know all those digits either 3 or 6, right? And I just want to make sure the total sum of those 5 digits must be divisible by 9. Who can tell me? How can I do my analysis, right? How can I find out those numbers? I'm not asking for the solution, but I'm asking like, how can I arrange my thoughts, right? So I can't just randomly 3, 3, 3. So 3, 3, 3, 6, 3, 3, 3, 6, 6, 3, something like that. That's going to be too not organized, right? We need to organize our thought. How can I organize our thought and try to find out what is the correct path for us to solve the problem? I'm not asking for the solution. I'm asking for the thinking process. How can I make my work, my analysis more well organized before I get what I need? Okay, so this time I'm going to ask, I know many students have the answer, but let's try to share the opportunity. So I'm always trying to ask some new students, everyone please get involved. So this time maybe I'm going to be asking maybe for Felix.
I think we can do some casework. So for example, so first we can have one digit as 3, then other as 6. Then like second, we can do like 2, 3, then like other are 6, and so on and so on.
Is that right? I think that's a very good idea. It's because there's so many 2, the 3s, the 6. If I just randomly do it, there's not a very well organized way. But let's try to do some casework. So this is where I talk about the casework. Let's try to talk about it in our 5 digits. How many digits are 3s? They could be 5 3s, 4 3s, 2 3s, you know, so on and so forth, right? They could be 5 3s, 4 3s, 3 3s, 2 3, 1 3s, or 0 3s, right? It is possible there's no 3s, right? So let's have a look at it. If you have 5 3s, so 5 3s, my next condition, I just want to make sure they're divisible by 9, right? Divisible by 9, aka means what? Means the total sum of those numbers will be divisible by 9. 5 3s, the total sum will be what? 15. 15. There's no way for 15 to be divisible by 9. So therefore, this is not going to happen, right? 5 3s, you won't be able to generate a number which could be divisible by 9. But what about 4 3s? 4 3s, and the other one will be 6, right? Plus 1, 6, because they only have 5 numbers. 4 are for 3s, and the other one must be 3. The other one must be 6. Then this guy will be what? 4 3s, 4 times 3 plus 6, 18. This one is good. 18 is divisible by 9. I don't know how I arrange all those 3s and 4s. Let's 3s and 6. Let's park it there for a sec. But at least I know 4 3s and 1 6 would be able to be a candidate. Okay? If you understand my point, can you do the same thing for these 4 numbers and tell me which of them or which ones of them could be a candidate for my solution? Please, everyone, get your hands dirty and tell me what it is. Because step number 1, you need to figure out, what are the candidates, right? Which numbers are good for you to do this analysis? Please, everyone. I see Camila already has the correct answer. But what about the other students? Please, everyone, get involved. A student asked, what was the question again? Yeah, that's the question. You can see the question. For how many 5-digit positive integers divisible by 9 could be written only using digits 3 and 6? Yeah, I see many students have the correct answer. I'm going to ask, maybe this time I'm going to ask for Caitlin. What are the possibilities, like for the candidates that works?
Only 1 3.
Only 1 3, right?
Yeah.
Perfect. 1 3 means there are 4 6, right? 4 6, right? this is quite understandable, right? You just check them one by one, and then you're going to find out most of them won't work, right? Are we all on the same page? Oh, good. You just basically check it one by one. Nothing too flowery. So that being said, there's only two candidates. One is 4 3s plus 1 6. The other one is 1 3 plus 4 6. Okay, so for now, the problem becomes how many integers I can create using either 4 3s, 1 6, or using 4 6, 1 3s. I'm going to write it here. 3 3 3 3 6. This is for one set, right? The other one is 3 6 6 6 6. How many integers I can create in order to finish such a work? This is a little bit counting problem, but not a big counting problem, right? So who can tell me how many numbers? Let's say let's break it into two parts, right? How many numbers I can create using 4 3s and 1 6? How many numbers I can create using 6 6? Are you using what? 4 6 and 1 3? Please. This is not a difficult problem, right? I want you guys to all get involved. Please, everyone, give me the answer, please. Yeah, I see many students have the correct answer. Yes. So I'm going to ask maybe Diane. What's that?
So the answer is that for each number, or well, the amount of numbers, it's kind of there's 5 numbers that you can make with those each, and in total that would be 10 integers.
Exactly, right? So okay, that's perfect answer. So why there are 5 numbers can be generated by from here? You can think the problem this way. You have 1, 2, 3, 4, 5 spots. You want to basically arrange this 5 digits, right? So basically from the 5 spots, the special number is 6, right? So from the 5 spots, you choose 1 for 6. For the remaining 4, you don't really care. They're all 3s. So basically C51, right? I don't know if you guys all know this counting, right? Counting, this is very important, right? So you just use the combination. You choose 1 from the 5, 1 position, give it to 6. The other 4 positions, you don't really care. Same thing here. You have 1, 2, 3, 4, 5. 5 positions, you just want to choose 1 for 3. The other, that will be automatically all 6. So therefore, C51 equals to 5. C51 equals to 5. 5 plus 5 is equal to 10. See? Easy peasy, right? This is a very understandable problem, right? But a very quick recap. You see, this problem is using exactly what we talk about it. You know, to solve a problem like this, you need to know the divisibility rule first, and you need to know some casework, right? After the casework, you're going to do some like enumeration. You list them out one by one, and then you are good to go. You see, this is like an easy problem, but I really want to take this problem to see, look, sometimes if we use whatever we introduced, we would be able to solve the problem fairly quick. All good? If all good, let's go to our question number 2. Let's go for an American problem. Previously it was Canadian. Let's go for an American problem. This is a problem that comes from 2015 AIME 2. question number 3. Okay, AIME is like you have to pass the AMC 10 in order to be eligible to go to AIME, right? This is American Invitational Math Exam. But this is question number 3. It's kind of like an easy one, not super, super difficult. So let's have a look at it. Let n be the least positive integer divisible by 17, and whose digit sum equals to 17. Tell me what the value of n. And let's try to highlight the word, be the least positive integer, no problem, divisible by 17, and whose digit sum equals to 17. Divisible by 17, I didn't really tell you guys the divisibility rule, right? I don't really know the divisibility rule for 17. So maybe I can't really find out like a pattern, what kind of numbers will be divisible by 17. Because, you know, even though I tell you 17, maybe this problem give you divisible by 171, right? So there's no way for us to cover all the rules. You know, we just can only cover some easy ones. For the difficult ones, maybe we need to think of some common strategies, you know, some so on and so forth. Okay, so let's try to think about it. Let's try to think about it. We want to find out it looks like these kind of numbers can be a lot, right? So like this kind of numbers divisible by 17, and the total digit sum is 17. Maybe not only 1 or 2, there can be a lot. So the question only asks you to find out the least, the smallest one. Think about it. If you want to find out smallest one of a number divisible by 17, and the total sum of all the digits goes to 17. You know what? Actually, my first reaction would be, let's try to think about it. Let's try to do some casework. Because it looks like this number can't be too big, right? It shouldn't be like a huge, huge number. A number can be divisible by 17, and the total sum is 17. Let's try to do some casework. So tell me, what kind of numbers could be divisible by 17? And we're talking about the digit sum. Apparently, let's try to talk about the total numbers of digits. A number divisible by 17 could only be either a 2-digit number, or a 3-digit number, or maybe a 4-digit number, so on and so forth, right? But let's try to start from the easy one. So this is considered to be the casework, right? 2 digits, 3 digits, 4 digits, because the problem asked me to do something, the least number. I don't think this is going to be something too big, too crazy, right? So let's try to do some easy peasy stuff. After I list out all the casework, let's do some enumeration. Because casework and the enumeration are always together, right? You list them out one by one. Who can tell me what are the numbers which are divisible for 17? And there are 2 digits for sure. And do we have any of these numbers? The total sum is 17. The total digit sum is 17. Who can tell me the first thing? Do we have any numbers? There are 2 digits. They're divisible by 17. And plus, their digit sum is 17. Do we have one? Please, everyone, get involved. Get involved and let me know. Do we have such numbers? You have to do some calculation. I don't think you can just guess them out right away, right? You have to think about it. And ask maybe, I don't know. Who gave me the answer already? Okay, I'll ask maybe Alex.
There are no multiples of 17 that are 2 digits that adds up to 17, or the digits add up to 17.
Is it right? You know what? You just list them out. There are not too many multiples of 17, right? These are only the multiples of 17 for the 2 digits, and none of them adding them together equals to 17. That's it. Now, what about 3 digits? 3 digits, yeah, there are many numbers for 3 digits, and they're the multiple of 17, right? So, you know what? I don't want to waste your too much time. I'll give you the answer directly. So you just have to list them out. There's no trick, right? You just have to list them out. See, that's the way. You just list them out one by one. All the numbers reach are 3 digits, and reach our and the total sum is actually 17. So what I can do is, because there's so many 3 digits, right? You don't have to list them out at one, like list out them all at one shot, because the question asks you what? The least. The question asks you the least positive integer, and their total sum is equal to 17. You just list them out from from like the smallest 102, and then every time you add 17, and you check the sum of all the digits, you find out this is the first one. 7, 40, 60, 7, 7, 476, excuse me. 7, 4, like 476. That's going to be a multiple of 17, and the total sum of all the digits equals to 17. That's it. And that's your answer, 476. That's it. So that's basically how you solve such a problem. Okay, how you solve such a problem. So no panic. Yeah, of course you want to take some time, list them out, but you just have to basically adding 17, everyone. This is not a rocket science, right? So it won't take too much of your time. And while you're writing, you'll be able to find out, okay, what are the total sum of all the digits? Okay, so that's the reason why we didn't really tell you what is the pattern a number could be divisible by 17. Because like I said, even though I tell you 17, tomorrow the question change go to 171. 171, what are you going to do? You're going to do exactly the same thing. 171, a multiple of 171, at least it's a 3 digits number. If that one doesn't work, you might go for 4 digits number. So that being said, you just have to list them out one by one using the casework. I'll say one of the most important thing is casework. Try to break them into different cases, and then you will be able to solve them out. So far, so good? Okay, the second one is more focused on the casework. All right, if all good, let's go to our question number 3. Let's jump back to our Canadian. Let's go for a Canadian exam. Okay. Let's go for question number 3. This is a problem from 2000, Waterloo Katie, question number 23. Okay, Katie has 25 problems. 23 is almost the last 3 problems. So let's have a look at it, how we're going to deal with such a problem, and how we use the technology we introduced to solve such a problem. So the problem says the leftmost digit, like the highest one, right, of a length, the leftmost digits of an integer of length 2000 digit is 3. Oh my God, you have a crazy number, 3. And then you have like, how many digits? 2000 digits. So here you have 1999 digits, right? You have a huge number, and the most left digit is 3. The total digit is 2000 digits. Okay? In this integer, any 2 consecutive digits must be divisible, either be 17 or 23. Okay? Any 2 consecutive digits. As long as they're adjacent, any two consecutive digits must be divisible, either be 17 or 23, either or relationship. And the 2000th digit might be either A or B. The 2000th digit is here, right? So this guy might be A or might be B. And then the question asks you to determine what's the value for A plus B. Of course, you need to get the value for A, get a value for B, and then adding them together. Okay, how can we do such a problem, right? We have a long number. There are 2000 digits. And the first bit, the most left bit is 3. Okay, and then you have 1999 digits. You really have no idea what they are. And the information says, the question says, any consecutive 2 digits must be divisible by either 17 or 23. So if you find such a number, you construct such a number, all the way, tell me the last digits. The last digit, the question tells you this up front. The last digits has 2 conditions, either A or B. So tell me the sum of these 2. All right. So it looks like it is impossible for me to find out such a number one by one, right? So it looks like the only breaking point for such a problem. Let's try to find out the breaking point. So this number has 3,000, 2,000 digits. I don't think that's a breaking point, right? And then the question asks you about the 2,000 digits, okay? But the most important question that the question gives you is that in any 2 consecutive digits, it must be divisible either by 17 or 23. Okay, I'm going to write it down. Divisible by 17 and 23. So this is a divisibility rule, right? But again, I didn't really tell you how the 23 or 17, this kind of divisibility works. So I don't think you can remember anything. But according to what we introduced in our AIME problem, as long as you get stuck, you have no idea how the divisibility rule works, what you're gonna do? If you know the rule, you directly list out the rule, right? But if you really have no idea what the rule is, I think the most straightforward way is just to list them out, right? Let's have some look at it, how this number divisible by 17, divisible by 23, how this number looks like. Because the good part is, for such a problem, you don't have to list out too many numbers, because the question says, for any given 2 consecutive digits. So it looks like as long as you list out the 2 digits number, which could be divisible by 17 or 23, maybe you're good to go. Is that right? Because the question just say, I need 2 numbers. If the question says, I need 3 consecutive numbers, then probably you're going to try the 3 ones, right? But there's only 2. So 2 digits divisible by 17, 2 digits divisible by 23. List them out. This is not a magic, right? I'm just going to help you list them out. 17, 34, 51, 68, 85. Okay, this is exactly the same thing as we write here, right? You see? All those problems, there's a lot of similarities there, right? They're American, Canadian, but you know what? the logics are very similar, like the numbers that are chosen are very similar. So having a good understanding for one problem will significantly helpful for you to do the other problems. Exactly the same thing, right? Just gonna list them out one more time. 23 is for the Canadian problem. That's for 23. 46, 69, 92, right? Because we only talk about 2 digits. We don't really care about 3 digits, 4 digits, so on and so forth. All right. Now, everything is listed. Everything has been listed out. Did you find something interesting for all those numbers? 17, 34, 51, 68, 85, 23, 46, 69, 92. It looks like all those numbers, the starting digits are all different. The first digits are all different, right? This is 7. Let me change the color. 7, 3, 5, 6, 8, 2, 4. We have a duplicate 6, but most of them are kind of like different. Okay. And the problem says every single digit of such a guy. This is my number, right? Every 2 consecutive digits of this guy must be divisible by either 17 or 23. And the question already gave you the first digit. So that being said, what should you do? Who can tell me? This is very, very conspicuous. You have already listed out all the possible candidates for 17, 23, whatever. And I have to make sure this number, every single digit, must be respecting your rule. 2 consecutive digits must be divisible by 23 or 17. And I know my number. The first one is 3. So that being said means what? Maybe you can ask for Camila.
The second one must be 4.
All right? Because
And
there's
the-
no way around it. There's only one number starting with 3. There's, if you want to put another number, like the rule will break right away. You don't have to wait for the other numbers. Okay, as long as the second is 4, then what about the third? The third must be what? Diane?
6.
6, right? There's only one 4. And then what's next? What's next? Phoenix?
8 or 9.
Yes. The next one, there's no guarantee because there are 2 numbers starting with 6. So that being said, you need to break it into 2 branches, right? So this is also considered to be a casework. What about my next one is 8? What about my next one is 9? Right? This is a casework. You break it into 2 cases. Okay, let's go for the 8 one. If I choose 8, what's going to be the next one? If I choose 8, what's going to be the next one? Don't look at me. Look at here. We have everything here. Alex?
5.
Okay. And then what's next?
1.
1. And what's next?
7.
And what's next?
Wait, there's no 7, so
There's no next, right?
I guess there's no next.
There's nothing. That's it. So it means that if you go for such approach, you're going to stop from here. But my question says this is going to be a 2000 digits number. So for sure, this one is wrong. You shouldn't choose 8, right? Because choosing 8, you only have like 7 digits, but you need 2000 digits. So that being said, you have to choose 9. Okay, choosing 9. Who can tell me what's going to be the next? This is very conspicuous. I have already give up the first one. Let's go for the second one. If I choose 9, 4, 6, 9. So the next one will be what? Kate, please.
2,
And then,
3,
and then,
4,
and then
and then it repeats.
6, 9, 2, 3, so on and so forth, right? Okay, that one makes sense because we need to have 2000. So that being said, let's have a quick look at it. That's going to be what? Change the color maybe to blue. Okay, so that being said, as long as you choose 9, this is going to be like a cyclic, right? 3, 4, 6, 9, 2. 3, 4, 6, 9, 2. Another 3, 4, 6, 9, 2. 3, 4, 6, 9, 2. So this number would goes like this: 3, 4, 6, 9, 2. 3, 4, 6, 9, 2. 3, 4, 6, 9, 2. So every 5 digits, you got a cycle, right? Okay. The question says, you need how many? You need 2000 digits. 2000 digits. So that being said means what? That being said means what? You starting from 3, right? This is one cycle, another cycle, another cycle, so on and so forth. All the way you go to, this is our what? How many? 399, right? You times 5, you have 1995. You have 1995 digits. And then the last cycle will be 3, 4, 6. Now you are almost approaching an end. So you can have some flexibility. You can write, definitely you can write 92 for sure, right? So that's going to help you to finish your 400 cycles. However, since this is the end, right? You don't really care this is continue or not. You can write 5, 8. Is that right? Because for the previous ones, you have to always write 3, 4, 6, 9, 2, 3, 4, 6, 9, 2, because as long as you go to 8, your cycling will stop. So you have to make it rolling, rolling, rolling. But all the way you go to your last cycle, because you're going to hit an end no matter what, right? So that being said, for last cycle, you can actually give some flexibility to these two guys. It can be 9, or if it is 9, you just keep repeating, that's it. Or you can choose 8. 8 is okay, because you're going to stop very soon, but it doesn't matter because this is going to be your 2000 digits, right? This is going to be your 2000 digits, right? The previous cycles you have to respect to make it rolling, but the last cycle you don't really care, right? As long as you can stop at the 2000, you're good to go. So that being said, the answer will be 5 plus 2 equals to 7. The correct answer will be 7. You see, we are using exactly the same strategy. Exactly the same. So what we did, we do some case work. I mean, we start with some enumeration. We list them out because I never tell you what is 17, what is 23. List them out. This is not going to kill you. And then you have to do some casework. This is the casework, right? You're going to break from 8 and 9, do some analysis. And then the following part is, all the way you hit the last digits, you can basically do some, flexibility. You have some flexibility to choose 5 or to choose 2. This is actually also using the same strategy we're talking about in our problem. So far, so good. Can I have some feedbacks? Are we all on the same page? Yes or no? All the students, are we all good? Perfect. If all good, let's continue. Now, let's go to a Chinese problem. I like to give you different problems from different countries. So this is a 2003 Chinese Western region Math Olympia problem. China is big, so they have like different Math Olympia pre-selections for the West, for the East. So this is an interesting problem from the West. Given positive integers, one, 2, 3, 4, 5, 6, 7, 8. Place these numbers on the 8 vertex of a cubic. Okay, a cubic has 8 different vertex, right? I put these 8 numbers on these 8 different cubics, 8 different vertex, such that the sum of any given 3 numbers on the same face is greater or equal to 10. Determine the minimum sum of 4 numbers on the same face. This problem looks a little bit long, but the concept is very conspicuous. I have 8 different positive numbers, 1 all the way to 8. I want to place these numbers on the 8 different vertex of a cubic. So we have a, let me change it. So we have a cubic, right? The cubic goes like here. It has 8 different vertex, right? I just have to place all those 8 numbers on this 8 vertex. Okay, but how can I place it? I'm not doing a random place. I want to make sure the sum of any given 3 numbers on the same face must be greater or equal to 10. My cubic has 6 different faces, right? Any given face, if I take a face, let's say I choose this red face, okay, on the left, on the very right? Any 3 numbers on the 3 different vertices, on the 4 different vertices, right? They must be greater or even to 10. The total sum must be greater or even to 10. Same thing. If I find another one, maybe like the one on the top, I pick up any 3 numbers, adding them together, greater or equal to 10. So if that's the case, how I do such arrangement? So what is the minimum sum of 4 numbers on the same face? Means we have 6 different faces, right? So each face I pick up maybe, like I find each face I pick up 4 numbers, I do add them together. I find another face, add them together. I want to find out what is the minimum sum of all the numbers on the same face. 4 numbers on the same face? How can I do such a problem? I think you can actually do some trials and errors. You can try to place the numbers one by one and hopefully figure out what it is. But trust me, you have like 8 numbers. If you really want to do the trials and errors, you're probably gonna have 8 factorial different combinations, right? If you really want to try them one by one, there are 8 factorial different ways. This is crazy. I don't think you can do that. If that's the case, maybe we need to do some analysis before we jump to the solution process, right? Let's try to do some analysis. Is there any way for me to kind of like expedite my calculation rather than least amount one by one, which is absolutely crazy, right? How can I find out the breaking point of this problem? Of course, I think very intuitively, I want to start with the condition given by the question, right? This is the only breaking point I can get started. Because the other stuff, they're not so informative. The only thing is, this arrangement is special. You can make sure the sum of any given 3 numbers on the same face will be greater or equal to 10. Okay. Maybe that's my breaking point. And then you want me basically determine the minimum sum of 4 numbers on the same face. So let's try to do such an interesting assumption. Suppose I have already found a face. With my number A1, A2, A3, A4. They reach the minimum sum. Okay, suppose I just find one. I don't know where they're at, but let's say I find a face. So this face, of course, has 4 numbers, and they somehow reach the minimum. And of course, the question says what? The sum of any given 3 numbers on the same face must be greater or equal to 1, greater or equal to 10. Let's say, suppose I want to make my life easier. I have A1 is lesser than A2, lesser than A3, lesser than A4. Okay, let's say I find a face. The face has 4 numbers. Their total sum is the minimum, and A1 is lesser than A2, lesser than A3, lesser than A4. Okay, does it make sense? Because 1, 2, 3, 4, A1, A2, A3, A4 must be different, right? They're coming from these 8 different numbers. Okay, according to our definition, any 3 numbers on the same face must be greater or equal to 10. So that being said, A1 plus A2 plus A3, they are the minimum 3 numbers, right? Their total sum is greater or equal to 10. Okay, so this is all given by the problem. Let me ask you one thing, a question for you. For these 4 numbers, A1, A2, A3, A4, they are chosen from 1, 2, 3, 4, 5, 6, 7, 8, right? And now you're telling me that A1 plus A2 plus A3 must be greater or equal to 10, according to this question, right? Then who can tell me? Who can tell me If three numbers, they're chosen from 1, 2, 3, 4, 5, all the way to 8, and you wanted me saying that adding them together must be greater or equal to 10, is there any constraint for this A1, A2, A3? They can't be too small, right? If you're choosing 1, 2, 3, of course, you won't be able to having these three numbers, adding them together greater or equal to 10. So who can tell me? To make sure A1 plus A2 plus A3 is greater or equal to 10, what is the minimum number, the minimum requirements for 1, 2, 3? I have three numbers, A1, 2, 3, right? A1, A2, A3. I know the total sum must be greater or equal to 10, right? And also I know they must be chosen from 1, 2, 3, 4, 5 all the way to 8. Is there any, just given these two conditions, do you have any kind of like a constraint? So is there something minimum requirements for A1, A2, A3? Let me give you another hint. If I really wanted you to determine the biggest number from the three, aka A3, right? A3 is the biggest number from the three. Is there any requirements for this biggest number? I think this biggest number can't be too small, right? Who can tell me? What is the special requirement for this minimum, for this A3, for instance? A1, A2, A3, A3 is the biggest, right? A3 is the biggest. Is there any special requirement for this biggest number? If it is too big, if it is too small, if there's something in between, how can we deal with that? I'll be asking for Galan.
I think A3 has to be at least 5.
Okay, why?
Because if it was any less, the sum of the other two, wait,
Mhm.
yeah, because A3 is the greatest of the three, we assume that. So if A3 was any less, then the sum of the other two digits will other two numbers cannot be well greater than 5 to make up 10.
Is it right? Because if A3 is 4, for instance, if this is A3, A1 and A2 must be lesser than 3. If this is A1, this is A2, 2 plus 3 plus 4 is only 9. So that being said, this is not possible, right? The minimum requirements for is A3 equals to 5. Let's say if A3, oops, sorry. If A3, oops, okay, here. If A3 equals to 5, this is A3, and then you have this, this is A1, this is A2, at least you can make sure A1 plus A2 plus A3 is equal to 10. Which makes sense, right? All right. So that being said, means in order to make such a requirement, your A3 must be at least greater or equal to 5. And don't forget, A4 should be greater than the A3, right? So if A3 is greater or equal to 5, Then what about A4? Who can tell me? What is the bottom line for A4? Felix?
6.
Right. A4 will be greater or equal to 6, right? This is very understandable. Okay. What the question is asking for you? The question is asking for you, what is the minimum sum of 4 numbers on the same face? Now, we suppose we have already found out such a special face, right? We suppose a face with A1, A2, A3, A4, they reach the minimum sum. And A1 is lesser than 2, A2, A3, A4. Now, you know A1 plus A3 is greater, A1 plus A2 plus A3 is greater than 10. Automatically, A4 is greater or equal to 6. So the sum will be equals to A1 plus A2 plus A3 plus A4 will be greater or equal to what? 16. Is that right? You just have to add these two things together. Right? You just have to add these two things together. Is that right? So therefore, the minimum sum of such a face will be 16. You see, using this analytical method, you don't really have to do the enumeration, but you can list out all the solutions like so understandable, right? So easy. Okay, so a student got a question. Can we explain again how A1 plus A2 plus A3 is greater or equal to 10? No problem. Because the question asks you, please try to find out a minimum like a face. So in this face, the minimum sum of 4 numbers is like the sum of the 4 numbers that is the minimum. So suppose I just find out such a face. I don't know where they are, but suppose I find out such a face. So this face, by any means, it has 4 numbers, A1, A2, A3, A4, right? And their sum is the minimum according to the question. Let's suppose these 4 numbers, there's a relationship. A1 is lesser than A2, lesser than A3, lesser than A4, okay? According to our question, the question says, when you do such arrangement, you want to make sure the sum of any given 3 numbers on the same face will be greater or equal to 10. It works for everyone. It must work for this one. And like I said, if you want to find out some numbers, the total sum is greater or equal to 10, and this like A3, which is the biggest number, can't be too small. We just do a quick analysis, right? We find out 5 is the bottom line. If it's more than 5, it's good. Lesser than 5, if you equals to 4, 2, 3, 4, add them together is only 9. If A3 is greater or equal to 5, intuitively, A4 will be greater or equal to 6. So the sum of all those numbers will be A1 plus A2 plus A3 plus A4, which is greater or equal to 16. You see, using the analysis, you would be able to get an answer without having all those enumeration, so on and so forth. But you know what? You can't stop from here. If you stop from here, it is correct, 16 is right. But for the sake of being rigorous, you can't stop here. Because if you just went to our inequality lectures, I keep saying, sometimes, even though you have such an inequality, but there's no guarantee that the minimum number can always be achieved. Okay, we have some old students come from the inequality lectures, you will understand what I'm talking about. Because if you only talk about, some minimum value, okay, yeah, it is possible that, you see, A1 plus A2 plus A3 is greater or equal to 10, no problem. and then you do some magic, you figure out A4 is greater or equal to 6, and then you add them together. Okay, you see, perfect. So 16 is the minimum number. Technically, 16 is the minimum number. That is correct. However, you really have to list them out. Maybe this is totally your imagination. Maybe there's no way for you to find such a number. Because in our last session, inequality and polynomials, we spent a lot of efforts talking about when you're talking about a minimum value, right? This is a minimum value, right? A minimum value of a, what should I say? A minimum number of inequality, it is not always guaranteed this value will be achieved. This is only like ideally, okay, ideally this is work, okay? You have two inequalities, adding them together, they're all good, but you really have to figure out they really, really exist. So this is a validation process. This is a validation process. So that being said, can I just find such a cubic? Let's say if you're talking about this is my minimum face, okay? This is the one which contains the minimum value. The minimum value is what? 16. If the minimum value is 16, it means what? I must have a 2, 3, oh, excuse me, not 2, 3. 2, 3, yes. So in order to have this minimum value, so I need to have something like this. Let's say, you see, A3 is greater or equal to 5. Let me choose 5. A4 is greater or equal to 6. Let me choose 6. And the other one, let's say I choose 2 and 3, because 2 and 3 plus 5 equals to 10. That's the minimum. So let's say I can find this is 3. This is 2. This is 5. This is 6. These are the minimum requirements, right? I want A1 plus A2 plus A3 equals to 10, and adding them together equals to 16. Can you have some quick calculation? Tell me, how can I find out the values for the other 4 different vertex? This is A, B, C, D. Who can tell me? What are the arrangements for the other A, B, C, D? If you can find it, and it fits the requirements, any other 3 numbers adding them together is greater or equal to 10, then your work is done. That's valid. If you can't find it, it means the total thing, the entire thing is totally your imagination. Okay, I'll give you 1 minute. Think about it. Who can tell me what is the arrangements? A, B, C, D. You only have like 8 digits. You already use 4. The other 4, you think about it, how to arrange them. If you can arrange them properly, then that's good. Yeah, I see a lot of students have the correct answer. And what about the other students? Please get involved. Try to do some quick calculation. like I said, as long as you indeed find such arrangement, means all your guessing is correct, that you can bump it up, right? If there's no way for you to make such arrangement, it means this is totally your imagination, and you won't be able to find such a solution for it. Yes. Maybe I'm going to ask maybe Rosalie. I don't know if I spelled her name correctly. Rosalie or something? I don't know if you, so I don't know how to spell her name. Yeah, if there's a E, I'll say Rosalie, but there's an A, because I'm more like using the French way, Rosalie. Anyway, yes. Okay, yeah, I mean, if you want to talk, yeah, you can talk. Otherwise, I'll find a different person. Totally, it's up to you. Yeah, there's no obligation. Don't feel bad. If you do not feel comfortable to speak, or if you have something wrong with the microphone, let me know, and we can always find another replacement. I'm gonna ask maybe, I don't know, let me see who, maybe Camila.
Yes. So my answer is A is 7, D is 8, B is 1, and C is 4.
Is that right? Yes. So this is actually one of the arrangement. You always want to make sure this arrangement works, and then you can wrap it up to say, okay, this is the correct solution. So therefore, 16 is the correct answer for such a problem. All right. So I think like these are pretty much all the problems I like to say. So as a quick wrap up of what we have learned today. Today is the first lecture of our number theory. We talk about the divisibility, which is quite an understandable topic. You learn it from day one, from elementary school. So how to have a good mark in the divisibility related stuff? You need to go for several very important strategies. So you need to know, basically, if you check all the problems, check it here, these are the strategies. So we need to know the factorization. In today's part, we didn't use too much skills about a factorization, but we're going to see that in more coming lectures. You're going to understand that the divisibility rule. Sometimes the rule is easy, I just tell you. Sometimes the rule is not easy, like 39, 55, right? There's no way for me to summarize everything. So try to do some enumeration. You just basically list out a few numbers, and then you can basically do the analysis based on that. And then in your entire divisibility, if not number theory related discussion, casework is always important. You can break them by different digits. You can break them by different cases. You can try to break them in different scenarios, but try to do some casework. From the casework, you might have used a little bit of counting here and there, but the goal is like the entire rule is I think it's very intuitive. Break them into different cases, try to find out a pattern for specific case, and then add everything together, you get what you need. Yes, I think this is basically what I want to say for today's lecture. And after the lecture, I'm going to upload our assignment into our Google Classroom, and you have 1 week to finish up our assignment. And in the next lecture, I'll be able to invite some student who did a good work for our assignment, and will be able to basically give us a quick presentation, show us what is our thinking process. The most important thing is that we need to do the thinking process. How do we think for such a problem? Rather than we just basically read answers one by one. All right, so that's pretty much what I want to say for today's lecture. You have any questions for me? All good? Okay, perfect. In that case, I wish you guys a good day. I'll see you guys for the next week. All right. Bye, guys. Have a good one.
Bye.
Bye.